Good morning, everyone. Let's get started. So the plan is to have a lecture today and on Tuesday, and then we'll be in the lab starting on Thursday. Make sense? Okay, so last time I talked about pulse width modulation. This was basically a way to produce an analog signal with a digital pin. We looked at some examples of that. Then I talked about interrupts, and I mentioned that the original chip that we used in this class, the Atmel 328P, had a one-way interrupt system where there was no kind of acknowledge back from the processor, and this introduced the problem of where if the peripheral kept the interrupt high too long, it would sometimes accidentally trigger two interrupt service routines, or if it didn't hold it high enough, you would only get one interrupt service routine. And then we talked about how more heavyweight processors have a acknowledgement that comes back, and this creates a three-way handshake where the peripheral requests an interrupt, the CPU acknowledges it, and then keeps the acknowledge high for the amount of time it takes to run the service routine. And then that indicates the peripheral when it can issue its next interrupt, right? And then we started talking about, we got into interface protocols, and there's high speed and low speed ones, and long haul and short haul ones, and parallel and serial. We talked about some of the other types of ways that these are differentiated. You have synchronous and asynchronous communication protocols. Synchronous has a clock in there, asynchronous doesn't. The faster ones, actually it's funny, the really slow ones like UART are asynchronous. And then the really fast ones like PCI Express are asynchronous, but the ones in the middle tend to be synchronous. And that includes two of the ones actually three of the ones we're going to talk about: SPI, I2C, and JTAG. Then I talked about SPI. It stands for Serial Peripheral Interface. I mentioned that SPI is not governed by any kind of a standards body. It's what they call a de facto protocol. So it's totally unregulated. And as a result of that, you see a lot of variations on SPI, depending on the chips you buy. It's kind of, it's not very consistent. The SPI is a master-slave interface where the master initiates initiates communication, and then it's expected that the other side cooperates with that. There's four signals, there's four wires that make up a channel. So there's S-clock, MOSI, and slave select, which are all outputs from the master, and then the slave kicks back one signal back to the master called MISO. So MOSI is master out, slave in, MISO is master in, slave out, and this creates a true full duplex bidirectional connection. So I can send and receive bits at the same time, even though that's almost never needed. SPI was, the understanding I have is that it was originally envisioned as this basically a shift register, a way to shift bits out of the master and out of the slave, and then after 8 cycles, they exchange an 8-bit word. So you send an 8-bit word to the master, and also while at the same time you're receiving one from the slave. So you're doing this kind of exchange. And so the physical layer of SPI is built on this concept of an exchange, whereas you have these 8 bits where you do this simultaneous read and write. And then I mentioned that there are 4 different timing modes. So in order to save power, the clock is dead whenever you're not actively communicating. And so what happens is when the slave select goes low, and this is active low, so when slave select slave select idles at 1 when the channel is inactive, and then when you want to activate the channel, slave select goes low, and the clock only runs while slave select is low. And then once the communication is finished, slave select goes back high, and the clock flatlines again. Okay. The problem though is that even though the idle state of slave select is defined as being high, the idle state of clock is not defined. It can be high or low, and that's determined by a parameter of the channel called C-pol, polarity, clock polarity, C-pol. So if C-pole is 0, the clock is normally 0 when the channel is inactive. And if C-pole is 1, the clock is, is high when the clock is not active, okay? So the important thing to understand about that is, depending on C-pole, that's going to tell you what the first clock edge is going to be during a communication session. And SPI is assumed to be an edge-activated synchronous protocol, much like a flip-flop is in a digital logic circuit. So when you're driving new bits, when you're changing the data bit, and when you're reading the data bit, you're concerned about which clock edge you're doing that on. It's all about clock edges in terms of the sampling of the data. It's all clock edge driven. That's important for SPI. And so if the C-pole is high, for instance, then you know the first clock edge is falling edge, right? Because it's going to go high to low, right? Likewise, there's a C-fa, which is clock phase, and that determines whether the receiving side, now remember, both sides receive, right? The slave receives and the master receives, depending on if you're talking about MOSI or MISO. But when it comes to the concern about SPI is that we want to avoid the receiver becoming metastable, meaning that the whole problem that SPI is trying to solve is that you don't want the driver changing the signal at the very same time that the receiver is sampling the signal, because that violates the dynamic discipline and it will cause the receiver's flip-flop, sampling flip-flop, to go into metastability and it will cause an error, right? Now, whenever you're using CAD tools like the ones we use in 611 and 313, those CAD tools, because all communication is happening on one chip, the CAD tools statically guarantee that you will never have that situation because they do a timing analysis and a timing closure. But when you have a communication protocol in which you have two independent systems communicating, it's a lot tougher to guarantee that you don't have this case where you're changing a signal and reading the signal at the same time. So that's what this is all about with SPI, right? So the C-fa basically says, is the receiving side going to read on the first or the second edge of the clock? Now the problem is we don't know what the first and second edge of the clock is because that further depends on C-pole, right? So if C-pole is 0, the first edge is rising, right? And so if C-fa is 0, then that means you're going to read on the first rising edge. You're reading on the rising edge, right? Likewise, if C-pole is 0 and C-fa is 1, then we're reading on the falling edge because C-fa of 1 means read on the second edge, right? Which would be falling if C-pole is 1, right? So you have to use both of those signals together, or both of those parameters together, they're not signals, both of those parameters together to determine what edge the flip-flops on the receiving side of the signal are sampling the data, right? And likewise, the sending side of the channel is going to be changing the data on the other edge, right? So if I'm reading on the falling edge, then I'm changing the data on the rising edge. Now that's important, and that's really the whole point of SPI. That is the most important aspect of SPI, is the fact that I'm going to write on one edge and read on the other edge. And so what that does is that maximizes the time that the signal is stable before and after the sample clock edge, right? So this presumably will guarantee that we will never go into metastability on an SPI channel and you'll never get an error. And that's the reason why there's no error detection mechanism built into this protocol, because it is robust by design, right? As long as both sides follow the rules, okay? So that's what C-pole and C-fa. Now, if you get them wrong, if the master is using one C-pole and C-fa value and the slave's using another, usually what happens, in my experience, and I've done this, most people that do this stuff have run into this. I've done it, and usually what happens is all of what you see is all the values that you receive from the master are shifted by 1 bit. That's usually how this manifests. But in the worst case scenario, you get just random errors on the master side because of metastability. Okay, so you have to make sure that when you buy a chip and you put it on your circuit board, you read the data sheet. The data sheet of that chip will tell you about what the C-pole and C-fa values are, And then you got to go to your code on the ESP32 or the Arduino and tell it what those values are. So the master generally is adjusting, or the master is the side is going to be accommodating whatever the slave demands in terms of these settings, right? So that's how this generally works. Okay, so in this case, C-pull and C-fi are 0, which means, now the way that you can tell, the way I tell, maybe this is a dumb approach, but the way I can tell, the dead giveaway for C-fa is all you have to do is look at the beginning. You look at the beginning of the exchange. If the data starts changing, like you see here, it's a don't care, right? This gray means I don't care what the data is, it could be anything. But the first transition of the data occurs 1/2 clock cycle before the clock starts going, before the first edge of the clock, which means the way that I describe this is my informal way of conceptualizing this, is if the data gets a 1/2 clock cycle head start on the clock, C-fa is 0. If the data and the clock start at exactly the same time, meaning their first transitions are together, then C-fa is 1. So that's a dead giveaway. Just look at when the clock starts versus when the data starts in terms of the first edge of each of those signals. If the data has a head start, C-fa is 0, right? And then likewise for C-pull, well, that's easy. Just look at what clock starts out, what the initial state of clock is. If it's 0, then C-pull is 0. If it's 1, C-pull is 1. Now, if I ask you on the quiz, which I think I do, make sure you take the quiz by Friday, by the way. If I ask you on the quiz or test, what edge of the clock is the data being sampled when C-pull and C-fa are 0, 0? That is, that's kind of hard to figure out. You have to think about it, right? If it's 0, 0, I'm reading on the first edge and my clock starts out at 0, so obviously rising edge, right? Rising edge is where I read the data. And look, the rising edge happens right in the middle of the transition points of the data. So the whole idea is that this protocol is bulletproof because this is going to be read as close to the middle of the transition points on the data as possible, right? Now, if you don't have this in a protocol, then you're probably going to need some kind of error detection, some kind of parity bit or something, because you're going to get errors. It's going to happen, right? If your phases aren't lined up right. Okay, so that's SPI. Now the problem is, and here's all 4. This shows all 4 combinations of C-pull and C-fa. So here's an example I might ask, again, on a question. C-pull is 1, C-fa is 1. What's the value sent? Okay, again, how do we know, C-fa is 1? How do we know that? Because see, clock, data, their first transitions are lined up. C-pull is 1 because the clock starts out as 1. Now, notice that I have these dotted lines on the timing diagram. Those are just kind of placed every clock cycle, but they don't necessarily mean anything. They're just a way to line things up on a timing diagram. So in this case, the dotted lines on the timing diagram happen to be lined up on the clock edge where we're sampling the data. So I added another set of dotted lines that bracket that, right? So I basically put lines where the data is changing, and then the sample is, so the red dotted lines show where the data is changing, and the black dotted lines are showing where you're supposed to be reading the data. And so at that point, you just have to look between those red lines and say 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1. So the data being sent is B5. And I also show here that it's most significant bit first, so we're reading from bit 7 down to bit 0 from left to right. I think SPI is usually MSP first, but it's, as I mentioned, there's no rules with SPI. There's no governing body. There's no standards. There's no standard for SPI. Like there's no IEEE SPI standard. Doesn't exist. I don't know where it came from. It was kind of organically evolved from people that were hacking on this stuff. So, but just to clarify, this is MSB first. Of course, if it was LSB first, you'd have to reverse the order of the bits. In this case, MSB first is convenient because you can read from left to right on the timing diagram, and so this would be B5. Okay, and again, SPI is always in multiples of 8 cycles because they're 8-bit words. It doesn't have to be 8, but it has to be a multiple of 8. Or, well, I shouldn't even say that, because technically you could abort an SPI transfer if the master just sends, slave select high. But I'm not sure if that's advisable. It might confuse your peripheral. Okay, so here's another example. Okay, so anyway, the terminology here gets a little confusing. So when you have this 8-bit transaction, it's not a transaction. See, I already did it. I already screwed it up. When you have this 8-bit communication, it's an exchange. As I mentioned, the idea is that the master and slave are supposed to be exchanging 8-bit words, right? The problem is that I have never seen a case where this was needed, ever. It's completely useless. I've never seen a need for true bidirectional exchanges for SPI. For JTAG, yes, but not SPI. So the physical properties of the protocol, which is based on exchanging data, is not really needed, because usually what you're doing with SPI is you're doing transactions. Okay, so there's the terminology differences. An exchange is swap 2 bytes. A transaction means I want to actually read something or write something from a peripheral using the same kind of style as the programmed I/O that we talked about earlier. So programmed I/O is where the CPU does a load or store instruction, which translates into a read or a write of an I/O register across the memory bus, right? And of course, that's a parallel bus typically. A memory bus is usually a parallel bus. SPI is a serial bus. But the objective is still the same. I want to be able to write a register on a peripheral, or I want to be able to read a register from a peripheral. Both of those things are not bidirectional. They're a half-duplex operation. Because if I want to read a register, I send the address, and Homeboy sends back the data, right? So when I send the address, half-duplex, because only one person is talking. When I receive the data back, half-duplex, only one person is talking. So there's no need to do this exchange business. It's pointless, right? It's completely ridiculous that we have this bidirectionality when we never need it. Likewise, if I want to write something, I send the address that I want to write to, and then I subsequently send the data I want to write to that address. And again, it's half-duplex, right? Only one direction. So I don't know why we're doing this. Why are we doing this? Why do we have bidirectionality here? It's pointless. Not only that, but the transaction part of this is actually an application layer protocol that's being built on top of the physical layer protocol of SPI. So SPI just defines the physical layer exchange mechanism, involving, what is slave select do and what is CPUL and CIFA. But the actual transactional level protocol is defined entirely by the application. So what does that mean? Well, again, you got to look at the data sheet. You got to look at the data sheet of your peripheral to figure out what transaction level protocol it's using, because it's not defined by SPI standard. And then you have to write a driver for your microcontroller that basically hacks SPI to achieve that protocol. So in this class, you're going to see different transaction protocols that work differently. It's not standardized, right? So the one that we're going to give you in Lab 1 is we made it up. We literally just made it up because the peripherals make it up, right? And then the one that you use for the actual peripherals on our board are different, right? So here's what I mean by that. So, so one way to do a very simple transaction protocol on top of the physical layer protocol is you can do 2 exchanges. The first exchange is like a network packet header where you send the address over, as well as a bit that says whether you're going to read or write, right? And then in the second exchange, you either receive data back from the slave if it's a read, or if it's a write, you send the data you want to write to the slave, right? So it requires 2 exchanges bundled together in one communication session, meaning that it's 16 cycles of slave select being down in total, right? Now that's kind of a minimum, right? In practice, you may have to do more than 2 bytes, two exchanges. But this is kind of the baseline version of it. So here's an example of that. And this actually came out of a data sheet Alex and I were just talking about this. This came out of the IMU's data sheet. And you'll notice that these signal names are not labeled correctly. It's supposed to be S clock, not SPC. It's supposed to be slave select, not chip select. It's supposed to be MOSI, not SDI, and MISO, not SDO. So why do they do this? Why do they change the names? Well, they're dicks, basically, because everyone knows it's MOSI and MISO, right? But like I said, because it's not governed by the IEEE, you're allowed to change the names, and that's exactly what they do, right? So yeah, so now we have chip select, but just keep in mind, just map in your brain that slave select. So that goes down, and then you have this, MOSI and MISO. Now, one of the things you'll notice here is that MOSI, or SDI, I don't even know what that means, serial data in, but it's in with respect to the slave, not with respect to the, okay, I don't even know why they call it that. But anyway, you'll notice that the MOSI signal, that should be called MOSI, is dead for half the time, and the MISO signal is dead for half the time. Well, because it's because you don't need both directions, right? So what you end up with is you send the address out, not just the address, but other stuff, right? Read-write selector and multi and signal selector, right? Multi and single. Multi and single. The multi and signal determines whether you're doing one word or multiple words. And read or write is obviously whether you're doing read or write. But now keep in mind that these are in the upper bits, right? That will not always be the case, right? This is not standardized. So for this particular peripheral, they want you to put the read and write flag in bit 7 of the first exchange. And then bit 6 is going to be the basically burst mode control, right? Single or multiple. And then you put 6 bits of address. Now you might say, well, wait a second, hold on. 6 bits, that's only 64 possible addresses. That's probably not a lot, right? Yeah, it's not a lot. A lot of these peripherals are pretty limited in number of, they don't have that many addresses, right? Although 64 still sounds small. But yeah, so then you put 6 bits of address, and you can think of this as your network header, your packet header. That's how I think of it. I think of it as the header packet. And then once this gets through, then you're either going to receive data back from the other side if it's a read, or you're going to just continue sending bits if it's a write, in which case this thing is going to be totally dead the whole time, right? Now you might say, well, wait a second, like why doesn't the slave send back like a acknowledgement or something? I don't know. They never do that. They should. Also, you might say like, what else? I mean, they could use this time for something, right? But yeah, they don't. They generally don't. So if I give you a timing diagram on a quiz or a test, and I ask you whether it's a read or write, it's very simple to figure that out. You know just by looking for these dead zones, right? If the MISO is dead the whole time, it's a write, right? Because nothing is sent back, right? And if you have a split where you have MOSI is dead for the second half, MISO is dead for the first half, well then it's a read, it's a load, right? You're reading, right? Very simple. You don't have to look very closely to figure that out, right? Now, one thing I asked when I first saw this is I was like, wait a second, there's an issue here. This thing doesn't have any flow control because once I send the last bit of the address, Homeboy has one cycle to start sending the data back. That's not a lot of time. What if the latency of accessing this I/O register is more than a cycle? Yeah, then you're in trouble because the master controls the clock, which determines the maximum latency by which the slave could start sending these bits back, right? So, but you have to stick to this, right? Now, again, if you only have 64 registers, that memory is going to be small enough that the latency should be small as well. The smaller the memory, the smaller the latency, right? It shouldn't take a lot of time for this guy. But it would be nice if there could be a back pressure mechanism where the slave could say, okay, I'll do it, but you got to give me a few cycles. I'll get back to you on this data thing. No way to do that in SPI, okay? Okay, right, okay, so here's a write operation. And again, this came from the data sheet of the accelerometer, or the IMU. In this case, they decided not even to show meso. I'm not even showing it because it's dead the whole time. And again, that's, I think, confusing. I don't like it. I don't like it. Don't like it. Okay, back to my timing diagrams, which are nicer. These, by the way, I generated these from Teaks from LaTeX. And they're a pain, but they look nice. In the following SPI transaction, assume the transaction address is stored in the least significant 5 bits, and the read-write flag is stored in the most significant bit. Notice that there's a bar over read, which means that's meant to indicate that read is active low, write is active high. So if that bit is a 0, it's a read. If it's a 1, it's a write. But again, that's arbitrary. You have to, could be anything you want. What is the transaction? Well, I can already tell it's a write because this thing's dead. Of course, then again, that's not to say that you can't send all zeros on a read. Like you could read something from a peripheral and it may read zeros, in which case this would still be dead. But if that were the case, MOSI would be dead. Its second half would be dead, right? Right? Unless, wait a minute, what if you read zeros, what if you wrote zeros? If you wrote a 0, then it would also be dead. So yeah, I guess there's corner cases here that might be confusing, but it's most likely going to be a write just because this guy's dead, right? Okay, so, but how do I know for sure it's a write? How do I confirm that? Well, it's the most significant bit of the first byte transmitted. If it's a 0, it's a read. If it's a 1, it's a write. Of course, it looks like it's a 1. I could tell it's 1 because this guy goes to 1 immediately. But to make sure, I have to look at where I'm actually going to sample this. So the clock and the data are transitioning at the same time, which means CFA is 1. Okay, that's confirmed. C-pull is 1, so I'm looking for C-pull is 1, which means I'm looking at the second edge of the clock. The first edge is falling, the second edge is rising, so I'm sampling on the rising edge. Happens to be the dotted lines are aligned on the rising edge of the clock, so that's good. So I could just look at where these black dotted lines intersect the data to read, right? And that the answer there is 1, right? So the first bit of the first exchange is a 1, and so it is indeed a write. Now, what is the address? Well, that's bit 7, that's bit 6, that's bit 5, that's the first bit of the address. So the address is 001, 00100. So that would be what, a 4? 4, right? 100 is 4, right? That brings me to here, which means this must be the first bit of the data, right? So this should be the 9th cycle, 9th dotted line. 1, 2, 3, 4, 5, 6, 7, 8. No, it's here. Oh, I was wrong about that. So I guess it's 8? 8, sorry. 1, 2, 3, 4. That's the first 4 bits. 1, 2, 3, 4. Sorry, I was wrong. The address is actually, it's not 4, it's 8. It's 1000. Then the data is 1011, which is B. 0101, which is 5, B5, right? So I'm writing B5 to address 8. Okay, all right? You get that right? Yeah. Yes, B5 to address 8. That's right. I did it right. Any questions about that? Yes?
Can you say what CPOL and CPHA are again?
CPOL and CFA? Yeah, so CPOL, so that together, those are designed to tell the receiving side of the connection what edge of the clock to read the data on, right? Rising or falling. And also which edge to start reading on after the transaction, or sorry, after the exchange begins, right? Well, no, in this case, I should say transaction, actually, because notice that the slave select is high, is low the whole 16 cycles, right? So, so if CPOL, I should have a table here. So if you have CPOL and CFA. And then this is read edge. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if C pull and CFA are 0, 0, I'm reading on the first edge. And the first edge is rising, right? Because I start out at 0, right? So this is rising. If CFA is 1, I'm reading on the second edge, which is falling, right? Because the idea is that I'm starting out 0, I go high, and then I go low. And that's the first edge, that's the second edge. So because CFA is 1, I'm looking at the second edge, which happens to be falling, right? If C pull is 1 and CFA is 0, I'm starting out high, I'm reading on the first edge, so boom, falling edge, right? So this would be falling edge. And if C pull is 1 and CFA is 1, then it's reading on the second edge, which means I start at 1, I go low, I go back high, so that would be rising. Right? So because again, so you have C pull is 1, starts out at 1, goes low, then goes high. This is the first edge, that's the second edge. So CFA is telling you what edge of the clock to go to, and C pull is telling you where the clock starts at, right? So C pull is saying where you're starting, CFA is first or second edge, right? And so using this table, you can figure out what edge I'm reading the data on, and then I'm writing the data on the opposite edge, right? So if this is the read edge, the write edge would be the opposite. So this is rising, falling, rising, falling, rising, rising, falling, right? Now there's an exception though. I notice that I mentioned that that first writing edge is a little weird. Yeah. The first writing edge is a little weird because notice that there's no, actually the first time I write, there is no edge, right? Because it's got a head start, right? This means that the master is setting the data bit before you even have a first edge of the clock, right? So how does it do that? I don't know. It just starts it out that way, right? And you might say, okay, yeah, well that makes sense for the master because it's the one actually driving the ship here. But what about the slave? How does it know? How does it know where to drive miso if it doesn't even have the clock? Well, I don't know. I'm guessing at the slave's just looking for slave select. So as soon as slave select drops, boom, it's got to get this guy ready as soon as possible. So basically the idea from the slave side is as soon as I see slave select dropped, I have to get my ass in gear and get miso set up as quickly as possible because you know the clock's coming, right? And the master is expecting to read on the first edge of the clock. And as a slave, I haven't even seen the clock. I haven't even seen the first edge yet. All I know is the slave select is down. So I got to get this guy, I got to get going here fast, right? I got to prepare miso. I got to get it driven and stabilized before the first edge of the clock, and I haven't even seen the clock go yet. All I know is that the slave select is low, right? So that's kind of the mechanics of this. So does that answer your question?
Yes.
Okay. But again, like I said, the whole point, I just want to reinforce this point. The whole point of this is that you're trying to get the signal stable. You want to have a setup and hold time. You don't want to violate the setup and hold constraints. Right? The setup says you got to have it stable before the edge. The hold says you got to have it stable after the edge. I don't know what the setup and hold time is because it's technology dependent. But if you follow these rules, you're going to get the best. It's optimized, right, for that, right? Okay. Okay. Then. SPI also will support what some people call burst mode, other people call streaming mode, and yet other people may call multi-byte mode, right? The idea is in the header exchange, you send the starting address, the first address of a multi-address transaction, and then you use another bit somewhere in the header, multiple, single, whatever. You use another bit to indicate that the address I give you is just the first in a series of reads or writes, right? So this way, you could like stream audio or something over SPI, right? You can basically say, here's the first address, and just give me everything starting at that address. And so in that case, the number of cycles is going to be 8 cycles for the header, and then 8 times the number of transactions for the payload, right? So in this case, this is 8 times 3. This should be 27 cycles. Doesn't look like 27, but it is. There's 8 here, and 8 here, because I am reading 2 consecutive bytes from the peripheral, okay? And the way I did that is I use this MS. I set this MS field to be 1, right? And you might say, how do you know it's 1? Well, because M doesn't have a bar over it, and S does, and M stands for multiple, and S stands for single, right? So that's just a multiple read. Yeah, so there's 3 exchanges in there. Also, notice this is weird. If this is a read, why is there data here on MOSI? This should be flat. These two from here to here should be a flat line. Right? Why'd they do that? Why'd they show it that way? I don't know. I have no idea. That's why I put question marks there. I don't even know what's that meant to indicate. I think when the old IMU guys were doing this data sheet, I think it was a mistake. I think that was a mistake.
Yeah, there were some mistakes in other places in that data sheet too, so that's what I think of as well.
So this is weird. This makes no sense. This should all be dead. Exchange 2 and 3 should be dead with respect to MOSI. Okay, here's a better timing diagram. So this is another example. This was me deciding that since I put the time in to write the code that generates these things, I was going to generate lots and lots of timing diagrams. But here is this is assuming the protocol from the IMU, right? Yeah, same protocol. It's not the same protocol we're going to use for Lab 1, though. You're going to use a different one for Lab 1. But this is the IMU protocol. So the address here is 0. Actually, oh yeah, that's right. It's this 1, 2, 3, 4, 5, 6. Yeah, 6-bit address, 2 control bits. Address is E. Read write is 0, which means I'm reading, and MS is 1, which means multiple, right? Now, you might say, well, wait a second, I have a question. How does it know there's 2? How do you know there's 2? 2 transactions. 2 reads, 2 read bytes. How do you know there's 2 read bytes? Like if all you can say is multiple or single, how do you know there's 2? Why not 3? Anyone have any idea? So I think the way this works is the reason you know it's 2 is because the master cut it off using slave select, right? The master ended it after 2, right? But if the master had kept slave select low, the slave would be expected to keep it going, keep sending bytes, right? But then you might say, well, wait a second, if that's the case, then why do we need the multiple and single bit at all? Why not just assume that if you keep slave select low in cycle 17, then you're obviously doing a multiple, right? Yeah, I don't know. I can't answer that. I have no idea. I don't understand that. But yeah, this bit actually, so in that sense, this kind of seems redundant, right? The multiple single. Okay, and the multiple write is there. I'll skip that. And here's another example of a write. You can see, it's a write because MISO is dead, so obviously I'm writing. So I'm writing multiple values here. MISO does nothing that whole time. Okay. Okay, sorry, that slide is misplaced, and I'll explain why. So let me just give you a quick summary, then that's all I want to say about SPI. SPI is very common, but it's very old. It doesn't make a whole lot of sense because it's based on full duplex, which no one uses. So it's a waste of a pin. It's 4 pins. You don't need 4 pins. But you don't have to pay royalties to anyone to use it because no one owns it, right? But the problem is that it's not very formalized. So it's single. Oh, also another big issue is that it's really designed for single master, single slave, meaning that really it's really just a point to point. It's just two ends of the connection, right? Which makes sense, right? Because there's nothing in the protocol that would indicate that you can target multiple slaves, right? There's no way to differentiate different slaves. And the address space is so small, right? I mean, like in that case, we only had 64 registers. That's only enough for one slave anyway, right? So it's really just a point-to-point type of... Now, there are ways that you can hack it to get multi-slave support, and I'll talk about those. But I've never seen a case of anyone using that. So it's 4 wires per channel. It has 4 timing modes. The physical layer is based on exchanges, not transactions. Transactions are built on top of exchanges. It's a de facto standard, and the upper protocol layers are defined by the application, right? So if you're writing a driver, remember I mentioned at the beginning of the class that this is all about writing drivers, essentially. If you're writing a driver for a piece of hardware, you have to actually deploy that application level layer stuff in your code. That's in your software, right? Okay, so now that brings us to Lab 1. So Lab 1 is, we'll start working on Lab 1 in lab on Thursday, next Thursday, but this does not require anything, really. You don't need the boards, you don't need the software. You can do this at home. A lot of students in this class choose to do this lab by themselves as opposed to doing it in a 2-person team, but you are allowed to do it in a 2-person team if you want. That's up to you. You don't have to come to lab. The reason you might say, well, then why are you allocating a lab session for this? Well, just so we'll be there so we can answer questions, right? If you have any questions about it. But you can start this early if you want. You don't have to wait till Thursday. It's due on February 6th, which is like 2 weeks, I guess, right? Most students find this lab to be pretty easy. So the idea is that we want to develop a software decoder for SPI. So SPI is, basically it's based on a parallel to serial conversion, right? You're taking a parallel data, you're serializing it into single bits, sending those bits across, and then there's some protocol stuff you have to worry about when to read and write the bits. So we're going to give you a trace file, which is like what you would get if you recorded a recording from a logic analyzer or an oscilloscope. It's like, signal voltages, right? You're going to read that file and then convert it into English prose describing what the transaction is doing, right? So really, what is this all about? What are you doing? What is the objective here? Well, it's basically you're just reading values from a text file and doing a serial to parallel conversion, essentially. That's what this is all about, right? You're reading bits and assembling them into a parallel variable in code, right? That's the idea. Okay, so now the signal trace file, how does that look? We developed it ourselves. It's our own proprietary format, but we provide an API to you to read it. You don't have to directly read it and have to worry about parsing it. Yeah, and then we also give you, and this is the greatest part of this lab, I think everyone appreciates this part. We also give you a script that grades it for you. It's a built-in auto grader. And the auto grader is based on hundreds and hundreds and hundreds of test cases that were synthesized for this project. So it has a really nifty way to validate the correctness. Okay, so that's the top level description. Let's talk about some details. So as I mentioned, we have a signal trace. You could think of this like a recording from, if you have an oscilloscope that can write to a USB thumb drive. It's basically, the idea is that you're sampling data and writing those samples to a file, a text file, usually a text file, right? Now the thing though is, there's really no point, and when we first developed this was kind of a thing we talked about, there's no point in sampling using a fixed sampling period. It's kind of dumb to do that. Because if the signals don't change, there's no reason to write the values of signals that aren't changing, right? So in the signal file, the samples are not uniformly spaced out. It doesn't have a fixed sample rate. It has a variable sample rate. So what I'm trying to show here is that if you have, now in this case I have 8 parallel signals along with the clock, so there's nine total traces. I only write whenever at least one of them changes. Now if any one of these signals change, I have to record that. I have to record all 9 signals anytime even one of them changes. But sometimes they don't change. Like here, we don't have a change for a while. They're all kind of DC. So we skip. We only sample it 5 milliseconds and then at 8 milliseconds on the next change, right? So the idea is that we wait until at least one of these 9 signals changes and then we write it to the file. And so this horizontal axis is the time axis and the red ones are whenever we have a change, right? So that's how the file looks. Now obviously your file is not going to have 9, you're going to have clock. You're just going to have the 4 signals that make up the SPI channel. Yes?
Why are you sampling at 0.015?
Oh, that's a good question. Did I screw that? I might have screwed that up. Oh, because the clock changed.
0.015.
Oh, 0.015 here. Oh, that's a good, yeah, I don't know. You know, I think it's been a while since I wrote this. What might have happened was I wanted to show that that's not always strictly the case. Sometimes you may have random writes in there. It's not a rule that you can only write on a change. That might be why. No, I think he's right. I don't think anything, because we had a change here and S7 changed. Yeah, this one, I think you're right. Nothing changed there. Yeah, I don't remember what the purpose of that is. That's a good point. Okay, so this is what it looks like internally. So this is a text file, and it just has a column for time, and then it has a column for each signal. The first line of the file is the number of signals. No, I'm sorry, the number of samples, 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 13. Oh, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, sorry. There's 12 samples. The first row is the number of samples. The second row are the column headers, signal names. The third row is the number of bits. Right? Now you might say, well, hold on, why would the number of bits ever be more than 1? I thought we're doing a serial protocol here. Yes, but we had another version of this lab that did have multi-bit signals that we got rid of. But we support multi-bit signals, but these all happen to be 1-bit signals. Now the confusing part of this, though, the format, is you'll notice that the columns you don't have a column header for time, which means that it looks like you don't have enough column headers here, but it turns out that it's just offset. There's no time, it doesn't say time up there, right? So you actually don't think of that as column headers, just think of that as a list of signals, right? So does that make sense? So it looks like there's a mistake here, but there's not. We just start with clock, which means that this is this guy's clock, right? So there's an implied time column, essentially. Okay, but you don't actually have to, read that file directly. We have an API, and it's actually in 2 languages. We have a C API and a Python API, depending on which one you prefer. So in C, and by the way, you don't have to use the API either. You can write your own. You can read the text file directly. We don't care. This is just meant to avoid the overheads of having to interpret the text file, right? Because that, to me, it seems like busy work, right? To write code. This isn't like, 145 and 146 and 240 where you're just programming for the sake of programming. We have a specific objective and, we don't want to give you busy work. So in C, we have this class called, our structure called waves, right? So you declare a handle to waves, and then you initialize waves by saying parse file, but you don't actually give it a file. This is a little bit confusing. You're going to give it standard in. Why? Because our testing script assumes that the input, which is the trace file, is going to be shoved down the throat of your program through standard in, right? So you want to use standard in here, right? If you don't use standard in, then our testing script won't work, right? So basically what I'm saying is type this verbatim, right? And then same thing here with Python. In Python, you would say my waves equals waves, and then you say my waves.load text sys.standardin.read. Okay? So that sets it up. Then once you've done that, there's really just two functions you have to worry about. There's a function called nextEdge and a function called signalAt. Right? NextEdge is, it's going to return a time. It's going to return the time of the next edge of a signal starting at a certain time. So in this case, I want to know where the next edge of clock is. But I want to start it at this parameter called after, right? So if after, say, is 10 seconds, I want to look at the first edge of clock after the 10-second mark on the waveform, right? And then you have the option of positive edge and negative edge. These are Boolean. So you can look for either the falling edge or the rising edge, or just the rising edge or just the falling edge. So these are Boolean parameters, right? Python has the same thing. And then once you find the edge, you might say, why are you so concerned about edges? Well, because, like I said, SPI is edge-based, right? Everything is edges in SPI, right? So you're always looking for edges in SPI. It's not true in I2C, which is the next protocol we're going to talk about. But in SPI, it's an edge-based, it's edge-active. So once you know a time, then you can read the signal at a time by just saying signal at, signal name, time. Okay? So what are you using this for? Well, obviously, next edge is used for the clock, but then once you find that time of the clock edge, then you use signal at with that time, but on another signal like MISO or MOSI, right? Does that make sense? So that's basically it, and that's it. That's all you have to worry about there. So we show the C and the Python version. Now there's a couple other features you can use. In C we have a log function, and in Python, so obviously as you might imagine, log writes to standard error. In Python you literally just write to standard error. There's no helper function for that. Okay, so now what is the protocol being assumed here? Because I mentioned that SPI doesn't have any standard protocol, so anytime you decode SPI, you're going to need to know what that protocol is. This one's a little different. So this one, we're going to associate bits 7 down to 2 with the address. So this is in the header packet, the header exchange, the first exchange. So the address is not in the lower bits, it's in the upper bits, the upper 5 bits. And then, upper 6 bits rather. And then the least significant 2 bits are going to be bit 1 is your read or write, and bit 0 is your single or stream, right? Single or multiple, single or stream. Multiple is this stream, same thing. And then, of course, you have the next 8, if it's a single, assuming it's a single. Okay, this is a single. If it's a single, then the next 8 bits are going to be the data. So this is a read. I'm reading from address 17, I guess? Yeah, address 17, read, single. So that's the first 8 bits. The second 8 bits is the data coming back from the other side, the peripheral. Make sense? And so what you're doing is that you're reading from hex address 11, which in decimal is 17, and the data being read is 1A. 1A. Okay, we're assuming most significant bit first, right? 1A. So when you read this, your software should print read 111A, RD address data. Okay, so this is just a decoder. You're seeing this, you're printing this. It's just decoding what's going on, right? Here's an example of a write. This one says write 3B39. Okay, so 3B. Why is it 3B? 3B. Right? Doesn't look like 3B, but it is because it's 6 bits, right? 6 bits. So you only have 2 bits of the first hex digit, so it's obviously 0 to 3. And then the second hex digit is 0 to F because you have all 4 bits. So we're going to write 3B, and the data is 39. Again, 3, there's 3, and there's 9. Okay, so this would be decoded as write 3B39. Okay, that's part 1. Oh, and also, CPOL and CFA are both 0, always, in part 1. Okay, then we go to part 2. Part 2, now you might say, why is it divided into parts? Well, it allows you to build up your code incrementally, and it makes it easier to grade it because basically the partial credit is assigned per part. So the streaming one is if you have a stream, so if the bit 0 in the first exchange, right, is 1, then it's a streaming, right? But instead of the accelerometer approach of streaming until slave select goes high, we have a slightly modified version here where if you do a streaming transaction, the second 8 bits coming from the master is the stream length, right? Which means that you basically end up with a 16-bit header, right? A two exchange header packet, right? Header, where in this case I'm streaming and I want to stream 2, right? And then, since I'm reading also, then the peripheral is expected to send 16 bits back, right? And so if that happens, your program should print read stream 24, which is the starting address, and then the 2 bytes that it read. Okay? And we made this up, but you're allowed to make this up when you do SPI. You can make up your own stuff when it comes to SPI. Not with I²C, but with SPI you can just come up with arbitrary rules. And then here's a write stream 34B07E. Okay, and then in part 3, we want you to be able to support all 4 timing modes with CFA and CPOL and CFA. And these values are actually going to come out of the wave file, the trace. So you'll retrieve CPOL and CFA will be DC signals in the trace file. So just read those signals and you'll get, in other words, as opposed to like having the user type them in or something. Okay, they'll be specified in the trace file, which means there'll be 6 total signals in all the trace files, but the CPOL and CFA you won't even read until part 3, right? You'll just ignore them. But I think all of the traces have those. So there's S-clock, slave select, MISO, MOSI, CPOL, CFA in all the trace files. Okay, any questions about that? Okay, so the lab sheet for this, which has a lot of specific details and information, is on Blackboard. There is also you might be thinking like, wait a second, like if you're thinking through how like you would work on how you debug this. You provide an API that gives data that allows me to extract data, but I never can actually see the data. Is there any way to visualize? Like the problem is that, you guys, like when I showed you these slides, like this is visualized. This is a waveform, right? But when you look at the signal trace, that's not a waveform. This is unreadable. So if you're debugging your code, how do you debug if you just have this? Well, we also have a feature in our software where you can generate a graphical waveform for a trace file. And the instructions for that are in the instructions for that are in the document. You might say, well, how do you do graphics? It uses a program called GTK Wave, which is a standard Linux Ubuntu thing. It's just a wave editor. It shows you a waveform. It's not nice. It's not as nice as ModelSim or AMD's XST simulator, even though they had a 40-year head start. But that's open source, so what do you expect? It's free, right? It's just a free tool for generating a waveform. Okay. All right. Next topic is UART. So the UART's interesting because UART is asynchronous. There's no clock. And so there's no way to define the phase. There's no way to know when to read the data, rising or falling edge. Basically, the way UART works is both the sender and the receiver somehow, usually through trial and error, agree on the speed of the channel, the clock speed, which is called the baud rate. So like if you plug something in, and UART's usually used for console, for printing text. Not always, though. Found out that drones are actually controlled with a UART connection, which an unprinted UART connection. Which sounds weird because if you have two electronic components that are communicating, why would they communicate in ASCII text if there's no human to ever read it or see it or use it or interact with it? Why wouldn't you use a binary connection, right? It also turns out that the ESP32's predecessor, the 8266, I think it was, it used to just be used as a Wi-Fi chip. Like it wasn't the central processor. It was just a Wi-Fi interface, right? So you would have an Arduino chip, and then you have an ESP8266, and the ESP266 would just add Wi-Fi capability to your Arduino chip. That was the old usage model. But the way that you would talk to the ESP8266 to actually do the Wi-Fi stuff was through text, UART. They called them AT commands, like a modem. I don't know why they did that. That's insane, because there's so much overhead in having to encode in ASCII. But anyway, but UART is just basically a text, usually used for text. So what you do is you set the baud rate on both sides to be a consistent value. And then the sender and the receiver both generate their own independent clocks at that rate. Make sense? What's the problem with that? There's a big, big problem with that. The problem with that is that you don't know what the relative phases of those clocks are. And so there is no way to guarantee that this guy is not going to be changing the signal at the same time that this guy is reading the signal, which is going to cause chaos. Right? So how do they get away with it? Well, there's two reasons they can get away with that. Number one, they run these very, very slowly. So the baud rate, which is the rate at which data is sent, is in the kilobits per second, kilohertz. Whereas SPI, I didn't talk about this one. I never mentioned what the clock rate was on SPI, but it's fast, real fast, megabits. I've seen SPI can go like 10 megabits, 100 megabits. SPI is fast. But this is slow. So what happens is the statistical likelihood of you entering metastability is a function of the clock period. If your clock period is small, like SPI, you are very likely to read and write at the same time. But if your clock period is extended and you have a very, very long bit time, then the amount of time, basically the ratio between the clock period and the edges is extended. You have a bigger ratio. So the probability of metastability goes down as you decrease the frequency, right? So what that means is that's why you can't run UART fast, because if you run UART fast, it increases the likelihood of a simultaneous read and write because of the phases being aligned. The probability that the two clock phases are aligned is increased. Make sense? But that's not good enough because eventually you're going to get an error no matter what. Even if you run UART slow, you're still going to get an error, right? And so for that reason, they have also provided the ability to detect errors called parity. So this is the reason why we're going to talk about parity here, where we didn't with SPI. SPI didn't need a parity because of the timing that it does, the edge timing. Whereas this guy needs parity because inevitably you're going to get errors on UART. It is not a question of if but when, because there's no phase management of the clocks. Okay, so basically UART is also just one wire for transmit and receive. So again, UART has kind of the same issue that SPI does. Remember I mentioned SPI has bidirectionality. We don't need it. Who needs it? This also has bidirectionality. We don't need it. You're never going to be typing at the same time the thing is printing, because generally with UART, the way it works is it prints a prompt and says hello, then you type a command, and then it prints a response, and then you type a response. It's like talking to ChatGPT. You never talk into ChatGPT as ChatGPT is talking, so there's no reason to have a bidirectional connection there. But they have it, I think just for simplicity, right? So, but the other problem is because there's no, you know how like SPI has MOSI and MISO that define the connections? There's a master and there's a slave. There's no master and slave with UART. So the other problem is that all you have is transmit and receive, which means that this guy's transmit has to be connected to this guy's receive, which means you have to do a null modem adapter. You have to cross over. You're always crossing over. But what happens if this transmit is connected to this transmit? Well, then it's broken. It doesn't work, which happens all the time. Very common mistake with UART is you don't cross over your wires. Right? Another common mistake that I make constantly is getting the baud rate wrong. The receiver is using a 9600 baud rate, and I'm using a 57,600 baud rate, and then it doesn't work. And you never know what the baud rate is. I never know what the baud rate is supposed to be. Never. Every single time I've ever connected anything to UART, I had to guess and use trial and error. Because you never know, it never tells you, it's never clear, it's always unclear what the baud rate is supposed to be. I hate that. And now there's lots of baud rates. There's like, you can go up to 115,000 baud.
I've even seen like the ESP32, it uploads at 900 something thousand. That's the
Oh.
biggest I've ever seen. But they can get insane nowadays.
So yeah, it used to be pretty much 96 or 57. Now there's lots of options, and I never get it right. I never know what to set that baud rate to. Yes?
Well, what's G&D?
Sorry? Oh, ground is ground. Yeah, this is indicating that there's a common ground. Now this is a little misleading because SPI also has a ground, but I didn't show the ground. So why am I showing ground here and I didn't show it for SPI? I don't know. That's weird and No. What this is indicating is that UART assumes that you have a ground-coupled system, but so does SPI. And I2C, right? Yeah.
Pretty much any protocol.
They all do. None of them support uncoupling until you go to a differential, like PCI Express and HDMI and DisplayPort and SATA. They use a differential system. So each bit is sent on two wires that reverse voltage relative to one another, right? Also, CAN, the controller area network that cars use, that's how your auto parking stuff works, like in your self-driving. That's also a decoupled bus, I believe. I don't think you need a common ground for that one either. Because the way that one works is it sends a 0 by shorting two wires and it sends a 1 by separating two wires. So it's uncoupled. But all the things we talk about in class are coupled, which means that there is assumed to be a ground. And I don't know why I'm showing it here in this picture. I think I got this from a book or something. So, good question. Okay. So UART is, got about 3 minutes. So I'll just introduce this and I'll finish this next time. So UART idles at a 1. So if you're not sending anything, you have a 1. When you want to send something, you put a start bit, which is where you drive the signal low for 1 bit time. What is a bit time? It's the reciprocal of the baud rate, right? So you agree on a baud rate, and then the period of the baud rate The inverse of the baud rate is a bit time, and that's how long you have to hold that low for a start, right? How does the receiver know you're starting? Well, because it's always looking for a basically low, right? When it goes low, that means it's starting. And then you send bits, and then when you're done, you put a stop bit in, which is where you put the signal up for 1 bit time, right? Each bit is held for 1 bit time. Now here's the other problem with UART. The number of bits that you send for the data is also not fixed. It has to be pre-agreed upon. It's called the data bits. And the stop bits are also not fixed. So you may require 1 stop. It's always at least 1. You have to have at least 1 stop bit, but you could also have 2 stop bits or 3 stop bits, right? But these are other things that the sender and the receiver have to pre-agree on somehow, even though there's no mechanism for doing that other than some poor schlub that has to figure it out, right? So you got to figure out the baud rate and program both sides with the right baud rate, or usually one side's fixed, the other side's programmable. And then the number of data bits and the number of stop bits, right? And once you have all that set up, hopefully you'll get some stuff printed, right? Or you could be like me and get garbage and I'm punching my keyboard. So that's basically, it's pretty brain dead. It's just 1 start bit, data, and then a stop bit. And I mentioned there's also a parity bit that we can add, but I'll talk about that on Tuesday. Okay? So have a good weekend.